Now, throughout the field of chemistry, we see things as having some very common classes of reactions. There's going to be lots of categories of reaction within these classes, and don't think that I'm using the word class as some sort of a fancy jargon. I'm just using it as a loose grouping term. Now, that said, not every textbook will show these, and I want to make sure that we all have that common language because it shows up in other textbooks, it shows up in other courses, and it'll show up in things like standardized exams. Now, out of these three common classes, let's talk about the first one as a combination reaction. Combination reactions do about what you'd expect. You have two molecules combined to form some new molecule, and we can see those are going to be reasonably common in our lives and in our chemical knowledge. So if you take hydrogen gas and oxygen gas and you light them on fire, you're going to get water vapor coming off of that and plenty of heat. That's going to be a common combination reaction, as is this bottom one. The bottom one is going to be the root of an acid-base reaction. H plus and OH minus yield water. Now, if we have things combining to form something in a reaction, we expect the opposite could be true too, right? And that's true. If we have one molecule breaking apart to become two or more, those are called decomposition reactions. Now, in both of these, I'm showing it as just two molecules combining. It can be more, and you see that right here. We have two hydrogens and one oxygen combining at the same moment. Well, here I've got one molecule, sodium azide, decomposing to form sodium metal and nitrogen. This is actually the same reaction as you use when you're deploying an airbag. And if you want, you can find a video of that online. Just search for airbag and sodium azide, and you'll get to see the detonation of that. Now, I recommend you pause the video for a moment and try balancing this equation. Okay, let's see how you did. Okay, we had sodium azide. Here's how I like to keep track of these things. I like to make a little table right here. I currently have one sodium. I have three nitrogens. On the other side, I've got one sodium, and I've got two nitrogens. Well, this is an odd number, and this is going to end up being an even number. So I know right away I'm going to have to at least get to some sort of an even number. I'll multiply by 2 now. I might need to go to a larger number later. When I do that, I end up having 2 sodiums, and 2 times these 3 give me 6 nitrogens. On the other side, I can balance it out really quickly and easily since we don't have anything else on here. This one's diatomic, so we have to make sure that we multiply it by 3. That gets me up to a total of 6 nitrogens. And for that sodium, if I go ahead and I stick a 6 in right there, or sorry, a 2 in right there, then I get the 2 to balance out right down here, and I've got a balanced chemical equation. Notice that we are in the smallest whole number ratio possible, so that's a reasonable balanced chemical equation. Now, for our last category that we're going to talk about here, we have combustion reactions. A combustion reaction is when you have two different things, and one of these has to be giving oxygen into this somehow. It's nearly always going to be in the form of O2 gas. There are a couple of times where you can do a combustion reaction with non-gaseous oxygen, but typically this is going to be the most common way to arrange it, but you will always form CO2 and H2O. Now, here's another opportunity for you to pause and try balancing this equation. Okay, let's give it a shot. Now, this is my most complicated molecule. I want to start trying to get it balanced up with everything else early. This is my simplest molecule, and it's where I'm going to want to finish things off because it's the one where if I make a change, I don't change any other atoms. So this will be the last one that I am going to fix. I have 8 carbons here. Let me go ahead and put an 8 right there. Now, let me set up that table again. I have carbon, I have hydrogen, I have oxygen. Right now I have 8 carbons, I have 18 hydrogens, and here I have 2 oxygens. On this side, I'm up to having 8 carbons, no other carbons there. 8 times 2 is 16 oxygens, plus 1 there is 17 oxygens. And then over here I have 2 hydrogens. Now, I'm going to have to multiply that by about 9, it looks like. So we'll go ahead and put a 9 right there. That's going to change my hydrogens and my oxygens. So let's go ahead and check where I'm at. I have 8 carbons still. I have 8 times 2 is 16 oxygens. 16 plus 9, that's not going to work out simply. So still, we'll go ahead and go with it. We have 9 plus 16 is going to give me 25 of my oxygens. And then for hydrogen, I'm going to have a total of 18. So everything's balanced, but I have to unbalance it because I couldn't get those oxygens to be balanced. And if I come over here, I can't quite do it. Now, what you could do as a waypoint is you could put in, just for the moment, a 12.5 here. This is doing it differently than I usually do, but it's something you can do. If you have that as a 12.5, yeah, 12.5 times 2 will equal 25. The thing is, we don't like to have half numbers in our coefficients. So what we need to do now is multiply everything by 2 so that everything's a whole number. So we'll have 2 of these octanes times 25 oxygens yield 16 carbon dioxides and 18 hydrogens. Now, I want to point something out. If in your reaction, suppose you're doing this in a car engine or something, you started out with 2 molecules of your fuel. You bring in 25 molecules of oxygen. And then what happens when you detonate it? You're going to have 16 plus 18. That's going to be 34 molecules. And you're going to have heat. So if you go from 27 gas molecules in a volume, and you jump it up to be 36 molecules of gas in a volume, 34 molecules rather, you're going to have a sudden expansion, right? It's going to be an extra 7 molecules. It's going to take up more space. On top of that, you're going to create a lot of heat. And we know that gases expand when you have heat. And so we do expect there to be a big volume change. We'll see that rigorously and mathematically when we do ideal gas laws. But we do expect from that this is probably going to have a bigger volume afterward. Now, we're not doing that now. I just wanted to lay the groundwork for that for later when you actually come to that in the videos.